In this video, we will learn how to solve a statically indeterminate problem using the law of superposition. This method is also known as the force method of analysis for axially loaded members. It is also possible to solve statically indeterminate problems by writing the compatibility equation using the principle of superposition. This method of solution is often referred to as the flexibility or force method of analysis. We will consider the same example that we discussed in the previous lecture, a bar which is subjected to a point load P and it is fixed at support A and B. To show how it is applied, consider again the bar in figure 4.16a. If we choose the support at B as redundant and temporarily remove its effect on the bar, then the bar will become statically determinate as shown in this figure. So here it says that we have two support reactions. One is at A and one is at B. So for this case we have only one equilibrium equation as we discussed in the previous lecture. But we have two unknowns. So we cannot find two unknowns from the one or the single equations of equilibrium. So in this case, by using the law of superposition, we take one of the support reaction, for example, the support reaction FB at support B in this case as redundant, and we will temporarily remove the effect of this support. The redundant means the extra thing which is making something indeterminate. So in case of structures, a redundant is that extra reaction which is making this structure statically indeterminate. So if we remove that additional reaction from support B, this problem becomes statically determinate, because now in this case we have only one reaction at support A and this reaction can easily be determined using the equation of equilibrium. So here what we do as a first step, we remove the extra reaction which is making the structure statically indeterminate, and due to applied load we will find out the displacement caused by this loading, which is delta P, and this delta P can be determined using the load displacement relationship, which is equal to delta is equal to PL over AE. So by using the principle of superposition, we must add back the unknown redundant load FB. Here we can see in this figure that now in the next step we will apply this removed force, which is the redundant force, back to the same structure. So this force will produce deformation in its direction, which is opposite to this one. But according to law of superposition, the summation of this displacement due to this redundant force plus the displacement due to applied force must be equal to the displacement of NB, which is 0 in this case. If load P causes B to be displaced downward by an amount delta P, the reaction FB must displace NB of the bar upward by an amount delta B, such that no displacement occurs at B when the two loadings are superimposed. So this is the law of superposition for this case, that in actual statically indeterminate structure the displacement of NB is 0, and it is equal to the summation of delta P due to applied load and delta B due to the redundant force. In other words, we can say that this force must displace this end in opposite direction by the same amount to that which is produced by P. This equation represents the compatibility equation for displacements at point B, for which we have assumed that displacements are positive downward. So here the downward direction is considered positive, and for end B it is 0. So which is equal to delta P downward, which is positive, minus delta B, which is upward in this case. So we can put the expressions for delta P and delta B. For delta P, it is PLAC divided by AE, and for delta B, it is equal to FB into L over AE. So here it is to be noted that because of this applied load, only this portion is under tension. So we will consider the length of this portion in this expression only. So P into LAC divided by AE. But this force is acting at this end and it is trying to compress or shorten the length of this whole bar. So for delta B, the length of the whole rod will be used, which is equal to L in this case. So put these values into this expression, we get this, and from here we can see we have only one unknown, which is FB, and we have one equation, which is the compatibility equation here. So from this equation we can find out the expression for FB. Now next step is to write the equation of equilibrium. So from the free body diagram, as in the previous lecture, this is the equation of equilibrium. If we consider the upward direction positive, FB plus FA minus P should be equal to 0. So we have already determined the force reaction FB here, so plus FA minus P. So from here we can find out the other reaction at support A, FA. We can write this length LCB in terms of L minus LAC. So this is length LCB, which is equal to the total length minus this length LAC. So we can write FA as P into LCB or L. So this is the procedure for the analysis of statically indeterminate problems using the law of superposition or force method. So here first we write the compatibility equation. So in contrast to previous method, we first write the equilibrium equations and then we write the compatibility equations. But in this method we first write compatibility equation and then we write the equilibrium equation. Okay, we will solve the same example that we solved previously. This is the same steel rod which is subjected to a force of 20 kN at point C. It has a diameter of 10 mm. It is fixed at wall A and it has a gap at this end of 0.2 mm between the end B and the wall B prime. So we will solve this problem by using the law of superposition. So first we will write the compatibility equation. So here we will consider the support at B prime as the redundant. Using the principle of superposition, we have the compatibility equation. So here we can see that we initially have a gap of 0.2 mm. When it is subjected to external force of 20 kN, this force tries to elongate this bar. So first this end will move by 0.2 mm and then it will come in contact with this wall at NB prime and then a reaction force FB will be developed. So we are considering that reaction force FB at this point as a redundant force. So temporarily we will remove its effect, or we can think that we are removing this wall. So what will happen? So this becomes a statically determinate problem. This force will displace this end towards right by an amount delta P. So this is a displacement due to applied load. Now in the next step, now apply back the removed redundant force which was at this wall at B prime. So when this force is back applied, it will produce a deformation or displacement in the opposite direction, which is equal to delta B. So according to compatibility equation, the summation of displacement due to applied load plus the displacement due to redundant force Fb must be equal to the displacement of this end, which is 0.2 millimeter in this case. So here it becomes the compatibility equation. It is to be noted that if there was no gap between this end and at the wall, then this compatibility equation must be equal to 0. That the summation of displacement delta P minus delta B should be equal to 0 in that case. So here the bar can move by 0.2 millimeter. So that compatibility equation states that the summation of these two displacements should be equal to 0.0002 meter. So we can write the expression for delta P and delta B. So for delta P, it is equal to P LAC over E, because this force is acting at point C. So only this segment is in tension, so we will use the length of segment AC, which is 400 millimeter or 0.4 meter. So P LAC over AE. This displacement delta B is equal to FB into LAB over AE, because this force is acting at this end and it is trying to contract the whole length of this rod, so the total length of the rod will be used. So here the length is 800 millimeter plus 400 millimeter, so in total it becomes 1.2 meter in units of meter. So it is 1.2 meter here. So if we solve it, so delta P comes to be 0.5093 10 raised to power minus 3 meter, and delta B is 76.3944 10 raised to power minus 9 FB. So put delta P and delta B back into this equation, and solve it. So we will have, or we will determine the reaction Fb equal to 4.05 kilonewton. So that is the support reaction, which is here. Now write the equilibrium equation. So for equilibrium equation, we consider this free body diagram. So we have this rod is fixed at A, so we have a reaction here Fa on the rod. It is subjected to external loading 20 kilonewton. It is acting towards right, and here we have determined force reaction at B equal to 4.05 kilonewton. Okay, so the equilibrium equation states that the summation of all these three forces must be equal to 0. Here we have minus Fa, because it is acting towards left, and we have considered the right side direction positive. So minus Fa plus 20 minus 4.05 kilonewton equal to 0. So we have one equation, we have one unknown. So from here we can determine the value of Fa, which is equal to 16.0 kilonewton. So these are some practice problems. You can practice by yourself. Thank you.